This is Jack Jackson. We're going to be looking today at this linear regression project that started out this unit. And hopefully you've already worked through this project yourself, but if not, you can follow along here, or you can use this to kind of check what you did with your project. So we had some real world data here where we had these years, every 5 years from, well, not every 5 years, but from 1960 to 1995, some data. And this is the concentration of carbon dioxide measured in parts per million in the atmosphere at a particular location. So we're going to actually think of these as x and y values. Actually, we're going to scale back the x's so that's the years since 1960. Now, hopefully, if you're working through this, you've already worked through one of my earlier videos on some introduction to Microsoft Excel, because I'm going to be using Excel with this. So you can actually open up this Excel sheet, which is found in Blackboard, just below the project, and use this to help you actually compute the numbers in the project. Of course, you could also compute these numbers just using a calculator and record the results on the project itself or on another piece of paper, but we can also record a lot of it right here in Excel. So this will be a good introduction or a good use of Microsoft Excel. And Excel formulas start with an equal. So I'm going to, in this cell, put equals, and I'm going to click on this number right to the left and say minus 1960. Let me try that again. Minus 1960. There we go. And we get that. Now the nice thing about this is I can actually hit here and copy it, Control C in Windows, and come down here and paste, Control V in Windows. And notice what it did. It says the formula was A5 minus 1960, but when I copied and pasted it below, it became A6 minus 1960, and then A7, and so forth. So what it really is doing is saying, take the cell to the left and subtract 1960, and that gives us our x values. Now if I copy these, I'm going to go down here. In a minute I'm going to need these here as the x, and I can go down here and say paste, not the formula, but paste just the values. And that pastes the values down there, which we may need in a minute. So we'll come back to that in a minute. Alright, so one of the first things we want to do is come up with a graph of this. So I'm going to use Excel to make a graph. And so I'm going to highlight my x's and y's, which are right here. And then I'm going to go to Insert and then Scatter Plot and just choose this first one, and we have a graph. Now I'm going to clean up this graph a little bit, which we may not have taken time to do in class, but we're going to do this now. So first thing I'm going to do is I'm going to get rid of that. We see some data values here, and in this case, when we have x and y type data, it's often good to have some other vertical grid lines as well. So if we go to, let's see, to Layout, it gives us some options here. For example, I want to do primary vertical grid lines on the major grid lines, so it's marking that out every 5 years, which is good. If I don't like what I see there, I can click on those grid lines and right click and say Format Grid Lines, and I can change the style of the lines and so forth like that. I can also click on the scale down here and right click on that, and I can say format that axis, and then I can, this is automatic, I can extend this a little bit. Let's say I want to extend this out in the future just a little bit further. So I can, instead of making this automatic, I can say, instead of going out 40, what if I go out 60 just to make it go out a little bit further? And I could start this at 0, and then my measure unit is 5, that's good. And let's leave it at that. And say close, and now notice our scale went out a little bit farther. So we have some control there. I can do the same thing here. So I can go to format that axis, and I can do some things like, say maybe I want to start at 300 and then maybe go up to 500. Okay, and maybe I want to mark it off. Let's see, that's 5 is too much there. Let's mark it off. Let's see what 10 does. That's a little tight, but that's okay. So now we have a graph there, and we can experiment with that. 500 maybe too big. Maybe just want to go up to maybe 400. So I can experiment with this a little bit and change this around. The main thing, of course, is that I see all my dots. Okay, let me experiment with a couple more other things. One of the things that we want to do is, okay, if you want to put data labels on here, we could put labels above and they give the actual numbers. That's an option. You can either turn that on or turn that off as desired. Okay. We can also, let's see, what else can we do? We certainly want to do some things in terms of a title. So anytime you have, so these are axis titles. So title, the vertical axis, let's do it with a rotated title like this. And let's title this. So this is CO2 concentration in parts per million, ppm. Whoops, misspelled there. Let's try that again. Okay, that looks good. Okay, so now we have that axis labeled. We can go down here and label the other axis. Let's see. And we can label this one as years since 1960. Whoops. Okay, and so now we have labels. We can also, we definitely need to add some kind of title. So we can put a chart title, and let's put it above the chart here. And we can put CO2 levels in the atmosphere. Okay, now a couple other things we can do just to pretty it up a little bit. I can click on this background here. And I can do it from there, but I can also do it from here. Format chart area like this. And so I can fill it in. Let's say I fill it in with a solid color. How about a red? There we go. And so now we have a nice looking little graph there. I can change the color of the dots. I can change the style of the dots. Okay, so I've got several different things I can do. I can go here and change the, I can move this around. I can also go here and change the size of it. I can stretch it out, or go back. Where are we? And change the way that looks a little bit. So let's go back a little bit. Okay, within here I can click on this and expand or contract the area inside the chart as well. So that looks pretty good. So there's our data. Okay, so that's just a little bit about how you can do some charting in Excel, which we covered a little bit in an earlier video as well. Now let's actually look at some of the dots here. So the dots here, notice that these are not in a straight line, but they're kind of close to a straight line. So the question is, which line is the line of best fit? Okay, so first of all, the task in the project says, well, what if we draw a line through these first 2 points? What would that look like? Okay. Well, let's remember, a line looks like y equals mx plus y sub 0. You might call y sub 0 b. So that's the y-intercept. And the slope is delta y over delta x. That is y2 minus y1 over x2 minus x1. So remember this from your college algebra class or one of your algebra classes in the past. So if we're going to use these first 2 points, our 2 points are 0, 316.9. and 5, 320. Well, the y sub 0 is the y when x is 0, so we know that's 316.9. The question is, what's the m? So we need to fill in the blank right there, right here for m. Okay, so we're going to use that. So this is 316.9 minus 320. Let's do it the other way around. Let's think of this. Let's go left to right. Okay, so 320 minus 316.9 over 5 minus 0. So we're dividing by 5. This is 3.1, I believe. Yeah, divide by 5. That's 0.62. So 0.62 is there. So that's our equation. Let's type that in our chart right here. So y1 is 0.62 times x plus 316.9. Now, just to show you this, I'm going to pull up a different program here called Matica. And in Matica, I'm going to enter some data. And I'm going to enter our data here. 0, 5, 10, 15, 0, 5, 5. 0 is 316.5. 316.9, excuse me. 5, then 320. 10, 325.7. 20, 338.7. 30, 354.3. And 35, 360.8. Okay, and we've got a dot as a round dot, and it's going to be red. Okay, so let me go back here, and let's take a look. Now, why don't we see any points? Well, because we got a poor scale. We need to go from 0 to 35, at least on the x's, and the y's need to change here. So if I go to View, Grid Range, this is like setting the x-min, x-max, and so forth in your calculator, your window settings. So let's say we can start at 0 to x, and let's go a little bit further out. Let's go 50. And we can start at, well, it looks like it's going up. So if we start around 300, that's going to be plenty low enough. And let's go up to maybe 400. Alright, now I can see my dots. One of them is there at the edge. Let me go out just a little bit more. Let's go a little bit to the negative. Alright, so now we can see our dots there. Now let's put in the line in this. It's real easy to put in a graph of a line, so that's why I wanted to do this. 0.62x plus 316.9. So we can type in y equals 0.62x plus 316.9. Now, as we knew, it's going to go through these first 2 points, but notice it misses the other points. In fact, it misses this last one by quite a bit. So that's not so good of a fit of a line. Okay? What if we took these two, the third and fourth point, and did a line through those? Would that be any better? Let's see. Okay, so we want to do the same process that we just did here, but now we're going to use the point 10, 325.7. That's our x1, y1 this time. Next to y2 is 20, 338.7. So again, we need to find the slope. 338.7 minus 325.7 over 20 minus 10. That's 10 there. I'm gonna use a little calculator stuff here. Of course, I could do this in Excel too, I guess, but let's just use a calculator. Okay, so we're wanting to do 338.7 minus 325.7. I could have done that in my head, I guess, but it's 13. 13 divided by 10 is 1.3. Okay. So it's y equals 1.3x plus the y sub 0. How can we find y sub 0? Well, plug in one of the points, like say 10 and 325.7, and solve for y0. So it's 325.7 minus 13, which is 312.7. So our formula is y equals 1.3x plus 312.7. Let's check that here. Y equals, what was it again? 1.3x plus 312.7. Y equals 1.3x plus 312.7. Now if we did this right, it should go through this point and this point, the third and the fourth points with the red line. Now, just looking at that, which of these two lines is a better fit? Well, I think you'd probably agree that the red one comes closer to hitting the dots than the blue one. Now, if you're just counting the number of dots it hits, they're both the same, because the blue one hits 2 dots and misses on the rest. The red one hits 2 dots and misses on the rest. But the amount of miss is a little bit less on the red one. So how are we going to measure that? Well, that's really one of the main points of this project, is how do we measure that that amount that it's missing, and how do we measure which one's a better fit? Okay, so let me fix this just a little bit, because this is, go ahead and pull these labels down here, because those were wasted squares there. Okay, so we're using the same x's, and we're going to use this formula to get different y's, new y's. So again, let's use Excel to do this. So let's make a formula, and we'll say equals, we want to equals 0.62 times this x value of 0 plus 316.5. Now the nice thing is if I copy this, Control C, highlight here, and Control V, and paste, notice it adjusts the formula. So where it said B6 this time, the next one says it says B5 there, then it said B6, then B7, B8. So what it's doing is taking the one that's 1, 2, 3 to the left, multiplying by 0.62 and adding 316.9, and that gives you exactly what we're supposed to do. If we did it right, this should come out to be exactly 320, so something's wrong here. What did I do wrong? Let's double check that. Minus 320 minus 316.9, 3.1 divided by 5.62. Okay, that's correct. Did I did? Right there. That's supposed to be a 9. Okay, so now copy that, paste it below. Okay, and we have that. Now, how far off are these? Okay, well, to find out how far they are off, we can say, here a formula, and say take the real y minus our y by the formula, and copy that, Control C, and paste it below, Control V. And so all of these points are above the real y's. The real y's are above the predicted y's, whereas these 2 points are right on. We could add those up, but what's going to happen is ones above and below are going to cancel out some. And how could we work this out? Well, if you remember, the way we did standard deviation and variance is we looked at the squares of errors. And so that's what we're going to do. We're going to take these guys here and square them like that. And we can, I'm going to copy that and paste it here. So now we're looking at the squared errors, just like we did when we did variance. And now we're going to add those up. I can put this sum button. Remember, we know sum is adding it up. And we're adding up. It can highlight the part we want. And there's the sum. That's called the sum of the squared errors, or SSE for short. Now let's do the same thing for our other line here. We had a different formula for this line. Okay, this one was 1.3x plus 312.7. Okay, so let's use that formula. Equals 1.3 times, now the x's are over here, so over here, plus 312.7, I believe it was. Okay, and we'll copy and paste that. And these points should be the same as the original. So this time, so their errors right here should be 0. So let's check it out. So the errors are going to be, the way I'm subtracting it is the original minus the predicted. So that means that the original is actually above the predicted line, because that's positive, of 4.2 units. These two are 0 right here, so those are actually on the line. And these are above, and this one is, that's way off. So what happened there? Oh, this is that's not supposed to be there. Okay. So again, in this case, the ones that miss above the line, which we can see. These two are above the red line. These two are above the red line. These two are on the blue. These two are on the red. These red ones here are above the blue line here. So our errors are all positive. But we could have some errors if we shifted the line. For example, we took that red line and shifted it up a little bit. We could get some negative errors. So whether they're positive or negative, we want to square them. So we're going to take this and square it, copy and paste, and then what do we want to do? We want to sum up that. Now look at what happens here when you're comparing the sum of the square errors here and the sum of the square errors here. This one was the red line, this one was the blue line that we were looking at earlier. And notice that the red line is a much smaller number than the blue line, so that in that sense it's a better fit. And this is how we measure the fit. We measure which one of these sum of square errors is less. If you look back at our other video in this section, it gives a nice demonstration of this, and you can see this visually, which will help you hopefully understand what's going on a little bit. So this particular project, we can see what's happening numerically, and we can do it with Excel to help us see how we can use Excel a bit too. Okay, let's see. Let's take these guys here and move them down there. Okay. Now, the question is, though, what's the best line that fits it? Which one, when we figure out this sum of square errors here, will be the smallest? We certainly got better by going from the blue line to the red line, but can we do better still? And how do we know when we got the one that's the best? Well, it turns out that it's actually a Calculus 3 project to come up with the method for this. So if you ever took a Calculus 3 class from me, we would do a project on this. But, obviously Cal 3 is not a prerequisite for this class, so we're not going to do that project for sure. But we can go over the method that this uses. And again, we're going to use Excel to work it out. It turns out, maybe not too surprisingly, that the line that best fits goes through the centroid. And the centroid has coordinates where the x-coordinate is the x-bar and the y-coordinate is the y-bar. In other words, the mean of the x's is the x coordinate, and the mean of the y's is the y coordinate, and it goes through that point. So we're going to sum these up, and we're going to divide by however many we have here, 6. Of course, I could have also just put in average of those, and it would have worked as well. But let me copy that and paste it here. And so now we have the x and y coordinates of the centroid. And so our line of best fit is going to go through that point. Okay? Now, here is the formula, or the formulas right down here in this box. These are the formulas that we use to find the slope and y-intercept of that line. Okay? In other words, basically we find the slope of the line, and then we just use the formula y equals mx plus b, we'll call it maybe, b sub 0, and then to solve for y sub 0 or b sub 0, we just plug in the centroid, which we know it goes through, and solve that, and then you come up with this formula, y sub 0 equals y bar minus m times x bar. So that's pretty easy. The one that's a little harder to find is the slope, and it uses this formula here. Now that looks a little complicated. We abbreviate the top as s sub xy, and we abbreviate the bottom as s sub xx. So let's look at how this works. So to get this, what we want to do is take each x sub k minus x bar. So we want to take we have our mean down here. So what we do is we take the x and we subtract from that the x bar, which is here. Now the problem is if I copy that and paste it, things give us problems, because when I go down here, it went from B19 to B20, which is what we wanted, but it also went from B27 to B28, which we didn't want. We want this to always be B27. So I put $1 in front of the 27. That forces it to always be in row 27, and actually this I can do it with or without it, but here I can put $1 in front of the B, and that forces it to always stay column B. So it doesn't change that number there, but if I copy that and paste it, now the formula works out correctly, because now it does B20, which is 5, and it subtracts the 16.6 repeating, and it gets this, and so forth. And this thing, notice it always stays B27, but the first part of the formula, if you look at the formula right up here in this box, right up here, okay, notice that, well, I didn't mean to do that. Let's see, fix that. As I move up and down here, notice that the first number changes, but not the second. Okay, I can sum those if I want, but I don't really need to. Now, if I do the same thing for the y's, I'm going to say equal this y, the actual y, minus the mean of the y's. Again, I want dollar signs there and there, so that it always stays cell C27 for y bar. I copy that and paste it. That's the difference in the y's. Now, for s sub xy, the numerator here, I've got these all figured out, the x sub k's minus x bars. I've got all the y sub k minus y bars. Now I need to multiply them. So here I can say equals, take this cell times this one right next to it, and that gives me the product. Again, I can copy and paste, and so these are all the products, and now I simply sum up those, and that's what's called s sub xy. So that's the numerator here. Take the xk's minus x bar, the yk minus y bar, multiply, then add them up. That's s sub xy. Now I also need s sub xx. So what that is you take the x sub k's minus x bars, in this case this cell right here, and square it. And we do that, copy and paste all the way up and down, and we add those up. Whoops. Got ahead of myself there. These cells, enter. And that's s sub xx. And so the formula for slope is you take the s sub xy and divide it by s sub xx. Why is it this way? Well, you need the Cal 3 project to see that, but this is the formula that it works out to be. Now, we can use a simple formula for y sub 0, or b, y equals mx plus b there. And so we can put this in. Well, what do we need to do? We need to say, well, it is y bar, which is here. Start off with a formula with an equals. Equals, click on this cell, y bar, minus m, which is in this cell, times x bar, which is in that cell. And there's your y-intercept. So our equation of our line, y equals, let me round off a little bit, 1.303 x plus 314.3. There's 4 significant digits rounding off. Now we claim that's a better line than either one of these lines that we started with up here, a better fitting line. In fact, we claim it's the best fitting line. So let's check it out. Let's find the errors down there. Okay, we can do it right here. So again, let's see, these are the same x's. So let's copy these and paste these values right here. Okay. Now, what's the y predicted? This is the y that's predicted from this equation. So this will equal, well, instead of, let's do them round off. We'll just say it equals m, which is that cell, times x, which is that cell, plus y sub 0, which is that cell. Now, a couple of these I want to fix in. I want to fix in the y sub 0, and I want to fix in the slope, but I don't want to fix in the x. I want it to change. So whenever I copy this and paste it down, I get that. Now, what would be the errors this time? I'm doing the same thing here that I did in these two original tables up here to find the SSE for this line. And so what is it? We want to take the the actual y minus the predicted y and work that out, and we get these are called the residuals. Okay, also known as the residuals. Okay. And let's square those. Square those residuals. Square those errors. Copy and paste and sum those up. Let's see how much better we got on this than what we had before. 14.5 roughly compared to 941 and compared to about 31.8. So 14.5, much better amount. And so that is the smallest amount actually that you're going to be able to make, that sum of the square errors. It's when this formula is the one that you use. Okay, so this is our, that right there is the equation of the regression line that we're after. Okay. All right, let's continue on. Now, how good is this line? How good does this line fit? How well does this line fit the data? Is it a good fit? Is it a poor fit? Well, there are a couple of ways we can measure that. We can certainly measure it as the sum of the square errors, but the only problem is the more data points you get, the larger that's likely to be. So we need to average it out some way, and we're going to actually work this out. And we need a couple more things here. So up here we figured out S sub xy and S sub sx. Let's do S sub yy. And the way that works is you take the y sub k, that's this y, minus y bar, which was down here. Make sure that y bar doesn't change when I copy my formula, so put dollar signs in front. Copy that. oh, I'm sorry, we've already figured these out. They're right here. So I just want to take that and square it. That one there and square it. And we'll copy that and paste it down. And then sum those up. And that's S sub YY. That's also called SST, sum of the square total. Okay. Now we can go down here and do a couple more things. We can look at our predicted values here on our given line, and we could take our predicted y minus y bar. Okay, where was y bar? It's up here somewhere, right there. And make the y bar fixed, and copy and paste. These are the differences in the predicted y's from the y bars. Square those. We end up squaring everything here. And we can sum those up there. So that's SSR. So it turns out that what we end up using is SSR and SST. So let me make those a different color. Let's say purple. So we use that purple one and this one here, this purple one up here. So we use the SST, or the S sub YY, and the SSR, and divide those. So this formula equals SSR divided by SST, which is this one. And that doesn't look right at all. These numbers don't look right at all. Let me try that again. Okay. So this equals, I squared the wrong thing. I need the y minus y bar. This doesn't look right either. Let's try this again. This should be the y predicted here minus y bar here. Okay, I think that looks a little better. I'm not sure. Yeah, that looks a little better. Okay, and square this. Okay, yeah, that looks better. Now, this number here for r squared should always be a number between 0 and 1. The way we interpret this is, the closer this number is to 1, okay, the closer it is to a good fit, okay, and if it's close to 0, it's a horrible fit. It doesn't really look like a linear pattern at all. If it's real close to 1, like 0.99, that's pretty good. So that tells us that the line is quite close to fitting this data. Okay, so that's kind of how we interpret that. Now we have the correlation. The size of the correlation is the square root of the r squared. And then, let's see if I can do this. The sign on it is the sign on the slope. Okay? So if the r value is positive, that's when you have a positive slope, and r value is negative, you have a negative slope to your regression line. But again, the closer that r is to 1 or negative 1, okay, the closer the absolute value of r is to 1, the better the fit, and the smaller the r is, or closer to 0 it is, the worse fit we get. And that's called the correlation, or the Pearson correlation coefficient. And so we have just determined that. Now let me show you a couple other things that you can do. First of all, I'm going to go over here where I have both of these lines graphed. I can take my data points over here and I can go to curve fit. Let me go to options first to make sure we do it. We can do polynomial and select a first degree polynomial and say find that line of best fit and go ahead and fit a curve to it. So that purple curve should be the same curve that we just came up with. If I click on that purple curve, it has some other stuff here about how it figured it out, but look at the beginning. It's 1.3031x. Let's look at that. Is that what we came up with? Where's our equation? 1.3031, same thing, x, and it should say plus 314.35 or so. 314.3492. 314.3492. Same thing. It's the same equation. And so when we graph this line here, we are graphing this purple line. And I think visually you can see that that seems like it might be an even better fit. Now it doesn't actually hit any of the data values, but it comes very close on all of them. These two are just a little under. This one's almost on. That one's almost on. That one's almost on. This one's a little bit over. But overall, that's the best you can make that, smallest you can make that sum of the square errors. So that's the best fitting line. Now, let's look back at in Excel, and Excel will figure out the line and graph it for you as well. Real easy. If you just want to find the line, you don't need to see all the steps and how it was figured out. There's a really cool thing you can do in Excel. Once you get a scatter plot, which you remember we did right at the beginning before we did any of these calculations, we can just click on these dots here and right click and say add trend line. Okay, and it gives, we want a linear trend line. We can even move it forward, so we can move it forward 10 units and maybe backwards, 5 or 10 units. Okay, and we can say display the equation and the r-square value on the chart. Okay, and close, and there is our line. I guess I should have gone a little bit further in the future. I think maybe I can. No, I can't. Let me click on it again and make that line a little bit. Format the trend line. Let's go a little further. How far do I want to go? I want to go another 15 more, another 25 here forward. Alright, that'll kind of fill up my screen there, so we can use this to predict out in the future. There are our values. Let's put that down here for perhaps. Maybe we can take this and work this out. Now I can also do things like change fonts, right? So if I want to choose a different font, or if I want to make it italic or bold, I have lots of different options there. So there's the equation of our trend line. If you notice, that's the same equation, maybe rounded off a little bit differently, but that's the same equation that we came up with, and that's the same r-square value that we computed by this whole process. Look down here again. So by this whole process, we came up with an r-square of 0.9914. 0.9914. Up here on this, its process is built in, 0.9914. Look at the slope, 1.3031. Look at our slope here that we computed, 1.30 right here, 1.3031. Okay, let's make that red. And then what's the y-intercept? Should be 314.35. Look up here, 314.35. And so there's the line of best fit, and that whole process is built in Excel. Now let's do the same thing on our calculator, because on the test you're not going to have Excel, you will have a calculator. Now I'm not going to do the whole thing on the calculator, but what I am going to do is clear this out. I'm going to go up here to my stat plot by doing second here. I'm going to go to plot 1, and I'm going to make it a scatter plot like it has here. I want my x's in list 1, my y's in list 2, and a mark. So that's what I want. To do that, I need to put my data in. So I go to Stat, Edit. I want to go up here and clear and enter. And go over here on Y2, clear and enter. Now, if I go back to my data here, here's my data. Okay, so list 1, I want my X's. 0, 5, 10, 20, 30, and 35. In my list 2, I want my Y's. 316.9, 320, 325.7, 338.7, 354.3, and 360.8. Now, if I typed everything in right, now I can graph it. I've already got my stat plot turned on, so if I hit zoom number 9 down here, which is zoom stat, I can arrow down to it. Since I know it's 9, I could just type in 9 right here. And that will automatically adjust my window to something that works. If I want to go a little further out, I can. Like, what if I want to go to -5 and I want to go to, 50 or 45 here maybe, and then maybe, I can go a little further down, 300, and then maybe go up a little higher, 400. And if I want to do that, maybe I want to mark this off in tens, and the X is off in, maybe in 5s or something. And now I can graph it. And there's my data. To get the regression line, what I do is I hit Stat and go to Calc, and we get the line of best fit number 4 right there. And if you have your stat wizards, we tell it X is list 1, Y is list 2, and we want to store the regression equation. Here I can get a couple different ways. On this you can go variables, right arrow to Y variables, choose function, and then Y1, and put it in there. If you have the newer operating system, it's even easier. Just do alpha trace, which is F4, and it'll pull up Y1 there. And calculate. Now, if you don't have the newer operating system, you don't have that coming up, then it basically just looks like this. Linear regression or something like that. And then you put in Y1, comma, Y2, comma, try again. Linear regression, and you put in L1, L2, Y1. So this is X's, this is Y's, X is here, Y is here, and this is graph. Where you're going to put it in to graph it. And hit enter, and you'll get the same thing as this. And notice, what does it tell you? Again, it tells us our A and B. A is the slope, B is the Y0, the Y-intercept. And it gives us both the R square and the R value. Now, what if you don't have the R square R value showing up on your calculator when you do this? Do this. You only have to do this once. Go to catalog, which is second 0. This is diagnostics. You can type in D here by just hit this button. I'll take you to the D's. And go down till you find diagnostic on. There it is. Hit enter and enter. And you don't have to do it again. From now on, the diagnostics are turned on. So now when you run it, you will see. So now when you run stat, calc, number 4, linear regression, and list 1, list 2, and Y1, and calculate, it will calculate the formula for you. So it tells you the formula, gives you the things. Now, not only did it do that, it tells you the R square value, so that gives you an idea how well it fits. It also, if you hit Y equals, notice it put our formula where we told it to in Y1. So now when we hit graph, it can graph the line along with that. Now, I can use the line now to predict values, say further in the future. Like I want to see what happens in the year 2015, according to this model. Well, let's see. Let's figure it out here. So 2015 minus 1960 is 55. So I can say do Y1 of 55, and it'll tell me. According to this model, this is what happens. So if that trend continued from this time period to today in the near future, 2015, then this is what we would come up with. So let's see what we have here. Another way to do it, of course, is to go to your table. Go to your table and do an ask table, and go in here and delete those and put in 55 and enter, or just do a table, do an ask table, but make sure 55 shows up in your table. Or you can trace it if your window's big enough. So our window's only going up to 50, but if I went to 60 here and graphed it, now I can go to trace. Now notice right now I'm on the stat plot, so if I trace over left and right, I'm going from point to point. These are the ordered pairs of the original data. But if I up or down arrow, I move to the line, and now I'm moving along the line here, and tracing, I can type in a specific number like 55, and it will go right to that point. You can see it on the graph, and it tells me that same Y value. So you can use this this line of best fit now to interpolate and extrapolate. Interpolate is when we use it to find values in between these data values, and extrapolate is when we go outside the data values. So we feel fairly decent about using it for interpolation. We feel not too bad about extrapolation, but not as good as interpolation if we're close to the data. The further we get away from the data, the less confident we feel that our selection is any good. So hopefully this video will help you a little bit with understanding how to work with Excel a little bit. Hopefully you'll understand a little bit about what we mean by measuring what is the best fitting line and how we measure that numerically, and then also how we complete this project, but then also how we compute that line of best fit, and then also how we measure that line of best fit to see how good it is in terms of what the residuals are, what the sum of the square errors is, and then in terms of the coefficient of determination R square and the correlation coefficient R. And then of course then how we can actually do this in practice using, say, our calculator or Excel without going through all the steps necessarily, but come up with the line and these measures of fit. The other videos give you a little bit more visual interpretation of this as well.